Now the advantages of three-phase induction motors is there's no electrical connection between the rotor and the stator. So there's no slip rings and there's no brushes, and as a result there's no friction, which causes oxidization, which means that the motor needs to be maintained on a regular basis. As a result, the application is vast in industries, as factories works on three-phase systems, and because of the high torque abilities of the motors makes them ideal for power tools. Now the characteristic curves of a motor when we compare the torque and the speed. Basically, those are my axes. This represents my percentage of speed measured in RPM, and this is my percentage of torque, which is my rotational strength of the motor. My graph would typically look something along those lines. We can see that my speed and my torque will have an increase, but as we get close to my maximum speed we will get a drop off in that speed. When we compare the speed, torque and the current, we will see we get something similar. As the speed increases, my current will increase, and then also you'll have that sharp drop off. Okay, now on this graph we can see a specific point, and that point there will represent full load. In other words, the motor is converting a maximum amount of electrical power into mechanical power. Now this variance over there between the current and the torque graph, that there represents my slip. Remember, slip is the rotational speed difference between the synchronous speed and the actual rotor speed. Regarding calculations, firstly is my synchronous speed. Synchronous speed is the actual speed of the rotating magnetic field. It's calculated NS is equal to 60 times the frequency divided by the number of pole pairs per phase. Okay, to calculate the pole pairs per phase, I say P, which is equal to poles per phase divided by 2. Okay, if we think back of the motor, we will have a north-south, 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 for example, but these two are one phase, these two are one phase, and these two are one phase. So we look at the number of poles per phase, and we see that if we're looking at only one phase, we've got 2 poles, and then 2 poles divided by 2 will give me 1 pole per phase, or 1 pole pair per phase. The rotational speed, or the rotor speed, that's the speed at which the rotor is actually moving. NR is equal to NS multiplied by 1 minus S, where S is the slip. The slip is calculated as the ratio ns minus nr divided by ns, and it is expressed in a percentage value. Now when we use this slip in this formula, our percentage, let's say we've got a 98%, sorry, a 3%, 2% slip, then instead of writing 2% over there, we're going to write 0,02, and that is how we use the slip in the formula. To determine the powers, we've got 3 powers in our motor. First one is apparent, same as with the other 3-phase systems we've looked at. S equals square root of 3 multiplied by VL times IL. Then true or active, P equals square root of 3 multiplied by line voltage multiplied by line current multiplied by the phase angle between the voltage and the current, or the power factor of the system. And finally, mechanical. Okay, that is the actual output power. So P mechanical equals square root of 3 multiplied by VL multiplied by IL, line voltage and line current, multiplied by cos theta, and we include the efficiency of the motor. Now, if you're given the phase angle, rather put this efficiency before the cos theta to avoid calculation errors on your calculator. Now the motor can be connected into star or delta. So for a star connection, IP equals IL and VL equals square root 3 times VP. Phase voltage times square root 3 gives me my line voltage. For delta, phase voltage equals line voltage and line current is equal to square root of 3 multiplied by the phase current. Efficiency is determined output power divided by input power, should be the same as input power minus my losses divided by input power, should be the same as 1 minus P loss over P in. Now when it comes to motors, remember, or as the rotor turns inside the stator, it is experiencing the magnetic field of the rotor, but it's experiencing the magnetic field of the stator, but as it rotates, there's current flowing inside the rotor, which causes a mutual induction to take place inside the stator. So the speed of the rotation will influence the voltage and the efficiency and the power that is actually delivered by the motor.